Welcome students to this fourth lecture of this PDE course, and in this lecture we are going to talk about some behavior of regular sturm Liouville boundary value problem. So if you recall, the equation which we are going to study looks like this: P of y prime whole prime plus q of y plus lambda sy equals to 0, right? And here we will be assuming P, Q, S, these are C infinity of I. What do I mean by this? Here we mean that all of these given functions P, Q and S, they are smooth functions on the interval I equals to AB, and we are assuming lambda in C. Now if you remember the last problem which we did the example, in that example we have actually assumed that the lambda is not in C but only in R. So we are basically not looking for lambda in C. Okay, so why is that? So these are some properties of some regular sturm Liouville problem which actually guarantees that we do not have to look at whole of C. So basically we can just restrict ourselves to R. So let's look at it. So before we go on doing that, we'll just define something called a orthogonal function. Okay, orthogonal function. Now I hope you remember what are called orthogonal vectors, right? So let's say a vector in R2, they are orthogonal if the dot product is 0. So similarly, two functions, they are called orthogonal if a dot product kind of thing for functions which we will call as the inner product, that will be 0 with respect to some function. So basically what is it? Let me write it down. Orthogonal functions on the interval I. Okay, that's the definition. And what is the definition? So essentially, let's say you are given two functions, right? So let me put it this way. Let's say that let phi of x and psi of x, these are the two functions, okay, and they are real integrable functions. Yeah, we are assuming real integrable functions. So basically we are assuming that they are Riemann integrable basically. Yes, on I, yes, and we say that these two functions, yeah, so phi and psi, these two functions, okay, phi and psi, yeah, maybe I can put it like psi are orthogonal to each other, orthogonal, okay, on I, and here I am just putting it like this with respect to this is called with respect to. These are the notations which I am going to use throughout the course. With respect to, okay, WRT, with respect to another function rho of x. Yeah, this function is always assumed to be positive. Clear? If and only if, see, this is the inner product I was talking about. So in the case of vectors, we just think of it as a dot product. So the inner product of psi and phi, this we will be defining as integral over I phi of x, psi of x, and then rho of x dx. If this becomes 0, yeah, so for two vectors, what happens if the dot product is 0, then that is basically orthogonal. Here for two functions, the multiplication of two functions with rho of x, that should be 0. Now here very important thing is rho has to be positive function, yes, and moreover we call this rho as a weight function. So basically we say it is orthogonal with respect to the weight function. Okay, this is some weight. Okay, now of course you do realize that as an example, yeah, we have already seen that if rho is exactly equals to 1 in I, in some interval I, then on minus pi pi, so basically the I is minus pi pi, that's your I, sine and cosine, right? sin mx and cosine mx, okay, the inner product of that is going to be 0 for all mn in n. You remember that, right? And similarly you can also talk about sin nx and sin mx, that is going to be 0 for m not equals to n. You remember we talked about it. So these are the examples. So basically they are orthogonal to each other provided the weight function rho is 1. Okay, right. With that in mind, we are going to define the norm of a function phi. Yeah? You remember we can talk about the length of a function vector, right? Similarly, we can define a norm of phi, which is basically, think of it as a length of a vector. Okay, so we define the norm of phi. Okay, so this is exactly the same sort of thing as the length of a vector. So that is integral over I phi square x rho of x dx to the power half. Clear? So this is your this is our definition of a, we call it a norm of phi. So this is called a norm of the function phi, norm of phi. Okay, think of it as a length of phi. Yeah, kind of. Yes. Okay, so similar situation, right? So now once we have that, we can move on to our theorem. The first theorem which we want to do is this theorem 1. So this is basically talking about what is the relation between the eigenpairs. We want to talk about the eigenpairs, right? So let's say that so we have two eigenpairs. We start with this. So basically this is our equation 1 and the boundary condition is 2. Clear? Okay, so 1 along with 2 has, let's say, two eigenpairs. So let phi j lambda j and phi k lambda k. Okay, some people write lambda in the first and then phi k phi on the second part. Doesn't really matter. So basically it is this, the phi is the eigen function corresponding to the eigen value lambda. That's the thing. Okay, so you can understand what I'm trying to write here. Two eigenpairs like this. Yes. Okay, let's say that you have two eigenpairs of the equations 1 and 2. Okay, of the equation 1 plus 2. I hope you understand what's happening. So we have this equation, and after solving this equation we have two pairs of eigenpairs. Okay, so the first pair is this and the second pair is this. See, j and k can be anything. It can be 1, it can be 2, some different exponent essentially. That's what I'm trying to say. Okay, right. Then see this phi j. So we want to see what is the relation between this phi j and this phi k. Okay, then phi j, yes, and phi k, okay, they are orthogonal to each other, orthogonal to each other, okay, with respect to the weight function, with respect to the weight function. What is the weight function here? S of x on I equals to AB. So basically on this interval AB. So what is the weight function in our case? You see this x, this s. Okay, so see this s is a part of 1 and 2, right? And depending on this x, we can get the two eigen pairs, the pair of eigen pairs essentially. Yeah, two eigen pairs. And what we are trying to say here is this: the two functions which you are getting, the eigen functions phi j and phi k, they are going to be orthogonal to each other, right? And that is with respect to the weight function s of x. Is that clear? Now you see, if I am writing something like this, then s of x has to be positive. You see, the weight function is positive all the time. So essentially Here, if you remember, while doing the problem also we have assumed that S is positive. Okay, so S is positive. Let's just put this assumption, huh? So this is an extra assumption, plus S positive. I hope this is clear. Okay, so with that in mind, we need to prove this thing. So what am I saying? You have two different distinct eigenpairs. If that happens, then you have to have they are orthogonal to each other, the eigen functions. Okay, so how do you get it? So let's say proof if they are both satisfy the equation, then you have this thing phi let's say I don't know, maybe I can put it as I prime whole prime plus q plus lambda I s, and then phi I, this is 0, right? This is for I equals to j and k. See, if you are putting I as j and k, this will be true because this equation satisfies this one, right? So though this particular so basically this particular thing which we have, what is it? Yes, this equation is true. Okay, now what I am going to do is, so basically I have two set of equation here. Yes, so I will multiply one, so multiply one, the first one. So basically for I equals to k, so multiply the equation, let me write it this way, multiply the equation I equals to k. So basically if I am putting I equals to k, you get a equation, right, with phi k, and the equation I equals to j with phi one second, this is with phi this is with phi, this is k, right? So this will be with j, and this is j, so this will be with k. Is it okay? So if you do that, you see from here what do you get? You get lambda j minus lambda k, and then you subtract and subtract and subtract. Then what do you get? Lambda j minus lambda k is phi j phi k. Okay, that will be equals to phi j, clear, and then p phi k prime whole prime minus phi k, and then p phi j prime whole prime. I hope this is clear. Okay, I mean, if it is not clear, please do it yourself, and you can see this is happening. You see this q term, q phi 1 phi k phi j, that is going to be getting cancelled with each other, so there is no q term. Okay, now this part I need you to check this. So this is very, very simple, but please check this thing. You expand the whole thing and see that one term gets cancelled out, and you get this thing. It becomes p of phi k whole prime phi j minus p of phi j prime phi k. I hope this is clear. Okay, so what am I saying? This particular term, you see these derivatives can be expanded, right? Yes, it is very, very easy to see that if you expand it, you actually end up getting that this becomes okay, not so you check this. Okay, one second, you check this part. So I should write it here. Check this part, that this becomes p of phi j phi k prime minus phi k prime one second, phi j prime, sorry, phi j prime phi k. Okay, and then the derivative of it, the whole derivative. One second, let me put it this way, the whole derivative of it. Clear? So this particular thing, if you expand it, will actually will end up getting this thing. Yes, this is a term. So you have to check this. This is a very simple calculation, and I am absolutely certain that you can do it. Okay. Now you see, if we integrate, so integrating both sides, So this is very easy actually. It's just some calculation. Lambda j minus lambda k, and then you have integral s phi j phi k dx, and this integral is of course with respect to I, and then you have this particular thing, the integral and the derivative get so basically it actually reverses each other, so it will be p times phi j phi k prime minus phi j prime phi k. Okay, and this evaluated from A to B. Yeah, this is how am I getting it? Fundamental theorem of calculus. If you remember, fundamental theorem of calculus. Okay, again let me explain what is happening here. Integral f prime, you remember, f of b minus f of a, right? A to b. This is what I am going to use here. Yes. Okay, so and now you see, if I extend this whole thing down, what happens? I get this one, p of b, and then this whole expression evaluated at the point b. What is it? This is phi j evaluated at the point b, and then phi k prime evaluated at the point b, minus phi j prime evaluated at the point b, phi k evaluated at the point b. Okay, minus p of a. Okay, again the same thing, phi j evaluated at the point a, phi k prime evaluated at the point a, minus phi j prime evaluated at the point a, phi k evaluated at the point a. Okay, it's just I'm just putting together all the boundary terms here. Now a small observation, yes, and this is a very critical observation which I want you to understand. See, up till here we did not use, one second, up till here we did not use this condition 2. So now I am going to use this condition 2. See, phi j and phi k both satisfies this equation and this equation, right? So I'm just going to write it down as, this is, let's say, a, the equation 2a, and this I am writing it out as equation 2b. Okay, maybe I can write it like this. It will be equation, this is the a condition, okay, and this is the b condition. Clear? Okay, so let's look at it. See, from to the second condition, b part, we get b1 phi j of b plus b2 phi j prime of b equals to 0. Yeah, and similarly b1, same thing happens for k also, right? K plus b2 phi k prime of b is going to be 0. Is it okay? Now we are without loss of, see, you remember when we talked about this equation, right? We said that in case of a, this expression has to be a1 square plus a2 square is not equals to 0, right? Otherwise we will not have the information at the point a, and also b1 square plus b2 square not equals to 0. You will need this, so either one of the coefficient should be non-zero. Okay, so without loss of generality, let's just assume this thing. So without loss of generality, we will write it like this. Let's just assume that b2 is not 0. It doesn't have to be. Even if it is not 0, doesn't have to be. No issues here. Okay. See, the thing is this. If b2 is non-zero, if this is non-zero, okay, we can multiply this term. So we can multiply this term with phi k of b, okay, and this term with phi j of b. If this is b2 is non-zero, you multiply this thing and subtract, and we can get it. You see, if you do that, it becomes phi j at the point B, phi k prime at the point B minus phi j prime at the point B, phi k at the point B. This is going to be 0, right? This is very easy to see. If B2 is non-zero, I can just cancel it out, extra terms, and then I can just write it like this. Is it okay? So B1 I will cancel it out, and since B2 is non-zero, I can just take it on the other side, and this is what I am going to end up with. Yes. Okay. Now similarly, yeah. See, it doesn't really matter because you do realize if B1 is not 0, we are going to get the other part. Yeah. So basically the same thing, just sign changes, and because this part is 0, so we are going to end up with the same thing. Yeah, it doesn't really matter. So similarly, for A also we are going to get the similar sort of thing. So for A, we are going to get phi j of A, phi k prime of A minus phi j prime of A, phi k of A. This is 0. Yes. Now you see from these two expressions. So I hope I wrote it like 2, 3, right? One second, let me just check. I have write it down as 1 and 2. So we have now 3 and 4. This is 3 and this is 4. So from 3 and 4, from 3 and 4, okay, what do we have? We have lambda j minus lambda k, yes, and then you have integral a to b, s phi j phi k is going to be 0, right? Why? Because you see this expression phi j phi k prime minus phi j prime phi k evaluated at the point B is 0, and similarly this whole thing evaluated at the point A is 0. So essentially this is this thing, you see, phi j phi k prime minus phi j prime phi k evaluated at the point B, this is 0, and similarly this part is 0. Yeah. So if this thing is 0, then this integral becomes 0, this expression becomes 0, right? So you see this expression becomes 0, and since phi j and phi k are distinct eigenvalues, right? Since lambda j is not equals to lambda k, yeah, that will imply that A to B phi j of x phi k of x s of x dx is 0. Is it okay? So hence they are orthogonal with respect to S. Okay. So with this we are going to end this video. In the next video we are going to talk about more properties.